In section 410, the last section of the chapter, we're ready to do some polynomial regression. All right, so in our first data set, we're looking at years since 1980 and the federal population of prisons. And we're going to count by, it looks like 0, 5, 10, up to 30 and 36. I went ahead and stuck this data into my Desmos window, and I'm going to zoom on it. Maybe. Zoom. Okay, lovely. Okay, so what I notice about this is my data kind of curves up and then back down. I'm not thinking quadratic on this because quadratic would be curving this way and then down. Let's see how it's curving the other way. The concavity is different. So a cubic is probably going to fit this better. Now, it would like us to try a first, second, and third degree curves. So first degree is our linear, second degree is our quadratic, third degree is going to be our cubic. So just some notes over to the side. For, let me move my book, there we go. If we're going to do linear, we know the regression by now as y1 approximately mx1 plus b. Quadratic, we know as y1 approximately ax1 squared plus bx1 plus c. Cubic, is going to have y1 approximately ax1 cubed plus bx1 squared plus cx1 plus d. And I could go to quartic degree 4 as well. And this one would be y1 approximately ax1 to the fourth plus bx1 to the third plus cx1 to the second plus dx1 plus e. Now, my e is kind of in the way of this graph, so make sure you got an e right there. And again, you can fix this pattern if you want to do a quintic to degree 5. Well, make sure you have a degree 5 term, a degree 4 term, a degree 3 term, a degree 2 term, a degree 1 term, and a degree 0 term. So you've got all the terms covered going down your polynomial. One last thing about this quartic, I want to emphasize this really hard to read E right here is a capital E. It's a capital E because I cannot use the lowercase e because it's Euler's number, like the base of the natural log. I can't use lowercase e. It's reserved. So make sure that if you're using E, it's a capital E. Or just skip E and go to F. Just don't use little e because little e is not a variable. Little e is a constant. All right. So let's try our models here. All right, they want us to do linear. Linear's not going to do a good job, but we will try it anyway. It's okay, so it's not terrible because it's got a 9 for its r squared and 0.9, but it certainly doesn't follow the curves of the data set here. So let's try quadratic. Do you think quadratic will be better or worse? Let's find out. Ax1 squared plus bx1 plus c. You know, it's not much better. The r squared is a teeny bit higher, but it doesn't follow the shape of the data. So it's no good, right? It doesn't get us close to the data. I don't think it's any better in the data set. And it gets me maybe closer to this one particular point. But then again, hold on. So the quadradic's not any better, so I was trying to say before that happened. Okay, so let's go ahead and get ourselves a cubic. So y1 is approximately, let's try it, ax1 to the third plus bx1 to the second plus cx1 to the first plus d. All right, let me turn the other two off because there's a lot of clutter going on here. And now, ooh, this model seems to follow the trends of the data. It's curving with the data set, so this model is a good fit. Now, they don't ask me to find a fourth degree model. but maybe just for fun, I will. Why not? So let's find a fourth degree model as well. Y1 is approximately ax1 to the fourth plus bx1 to the third plus cx1 to the second plus dx1 plus e. Okay, now out of these two models, the quartic also follows the data set very well. Now, you might say that the quartic is a little tighter to the data. And I could do another one. I could do a quintic. I could do a degree 5 or a degree 6 or a degree 7. Every single time that I increase the exponent, no matter what, it will make the r squared value higher. Even with our linear and our quadratic, you can't argue that quadratic fits this data set better. It doesn't. They're both the same, but the r squared value got higher because the degree got higher. So you can say that yes, the quartic fits a teeny tiny bit better. It looks like it hits data points. It doesn't. If you zoom in, they won't actually hit them. But what we're going to have to say is when the shape stops changing, don't go higher. So because the shape of this model inside the data set is the same for the cubic and the quartic. So starting at the first data point, we're increasing, then we start decreasing. That shape is the same right here. We're increasing, we're decreasing. The shape of the model does not change within the data. Outside the data, the shape changes. There's a huge difference between the left-hand side of the cubic versus the left-hand side of the quartic, of course. But if you're looking at it just inside the data, there's no shape change within the data. So use the simpler model because it will never stop getting better. A quartic is better than a cubic. A quintic is better than a quartic. A degree 25 is better than a degree 24. There's never going to be a stopping point. So we need to stop as soon as we start to notice the shape does not get any better when I improve the model type. So there's definitely a shape change between the quadratic and the cubic because the curvature of the data, this one is curving upward, this one doesn't even curve downward to match the data set. There's definitely a shape change here. So we would not go with a quadratic, we would go with a cubic. So I'm going to write the cubic model down. Okay, so let's write this one down. I didn't write down the first and second degree. You can see their parameters up here. You can write the equations down if you wish. But for the cubic, this one would be y equals negative 0.0129. I'm using 3 significant figures here. X to the third plus 0.633 x squared minus 1.440x and then plus 27.636 as our constant. That's our cubic model. All right. Which of these curves best fits the data? It's the cubic. And I already wrote it down. What's the practical domain in this situation? Okay, so the practical domain is, well, we're starting with 0 as our starting year in 1980. And our data set went up to 2016. But based on the trend, it's a real short trend. I don't know, since most of these were increasing, there's a one set of decreases here. I don't know for sure that it's going to decrease. I don't know that it won't turn increase, right? So I'm going to go a little past the edge of the data set, but not too far. Maybe I'll go to 40 to say, like, I don't have enough info to really tell if this prediction going down here at the end is a trend or not. I'll make a prediction, but I'm going to lose reliability real quick on this. So maybe I'll put 40 just to not go too far past the edge of the data set. Okay. Domain's a little iffy. We need to just think about the situation, think about what we know about the data, and try to make a determination about what values for input will make sense in context. Okay, practical range. All right. The lowest value that we were given intel about was the 24.6. The highest value that we were given intel about was the 210.2. So I'm going to use a combination of the model and the data. I don't actually go below the 24.6 in the model. I don't actually go above the 210 in the model. So I'm going to use the data values to help me with my range and say my range is going to have a lowest value of 24.6 and a highest value of 210.2. My model does, of course, go down below. It goes down into the negatives. It's just not going to make sense in terms of this model. And the further I get down, even here to 0 or down to 15, I'm so far away from my model that I will have broken down by that point. So we'll use the data set to help us with our range here. And we're going to say that it's between 24.6 and 210.2. All right. Now I've got a new situation to look at. And I've got my data set over here. Let's zoom over on it. This is data on revenue of quick service restaurants in the US. Ooh, interesting shape here. I see a wiggle, and that wiggle makes me think it's going to be cubic. I bet we're going to get to try all of the functions. Do we believe that linear, quadratic, or cubic would best fit the data? Haven't asked me to do the regressions yet, but I think cubic. And I think cubic because I see that wiggle, that swish shape, that cubic shape will best fit the data. I don't want it to be a straight line. I don't want it to be a parabola. I don't want it to be a W. I want it to have that one little wiggle that my cubic function has. So we are going to get a cubic function. Now, we're going to get all of them because it asked us to. So just to save some time, I'm going to copy paste my models, my regressions from my other one. There's my linear. It's not terrible, but it doesn't give us a wiggle. Let's look at our quadratic. The quadratic almost is the same as linear. It's not if you zoom out, right? Because it'll eventually be a parabola. But over the data set, you get no advantage for quadratic. It doesn't give us a wiggle. So let's try cubic. Now, when the shape changes, I'm going to know that this model does something good. Okay, those two models gave me no advantage. My shape changes here. I was expecting a cubic wiggle to do it. Cubic wiggle, woo, looks nice. Now, maybe quartic? Let's find out. Does quartic give us any additional advantage, a new shape change? No. Inside the data set, it has the same cubic wiggle. It changes after the data set, but inside the data, it's the same. No advantage. Cubic already did a very good job, so leave it at cubic. We would only want to change to quartic if we needed an additional wiggle or if we needed it to have that turning point the quartic was going to have that the cubic didn't. So this one's going to be a cubic. Okay, find all three models, write all three, record the best fitting. Okay, so just have to write down the last one. I was only going to write down anyway. Okay, so the A value is 0.0193 x cubed. It wants three places. I'm going with three significant figures. Perhaps on my math lab you would round this as 0.19, but I'm going to make sure I have three significant figures here. And then minus 0.644 x squared plus 9.177x plus 144.347. That's our cubic model. Use the model to predict the revenue of quick service in those 2 years. So I'm going to rewrite my function and make sure that I have a sufficient rounding to get close to the model. So I've got my x cubed term, then I need a 0.644x squared term, and I need my 9.177x term and my 144.347. Oops, that was supposed to be point. There we go. Okay, so as you can see, it looks good. What I've typed was enough figures. I'm gonna take this 3 off for a second. is a little better with the 3, right? So I wanted my 3 significant figures. Otherwise, I do have a little bit of error that I don't want to see on my model. So I'm keeping the 3 significant figures. Now I'm going to make my predictions. This data was in years since 2000, so it's easy to compute that we want to plug in 25 and we want to plug in 35 for those two. Okay, so our f of 25 is 272.83, and our f of 35 is 504.13, and these are both in billions. $1 billion, actually, both. Okay, so which prediction do you have the most confidence in? So I'm going to actually graph these as ordered pairs. So this would be the ordered pair 25, comma, f of 25. I'm going to label that one. And then the other one would have been the ordered pair 35, comma, f of 35. And I'm going to label that ordered pair and zoom out till I can see them. All right, so I forgot to label it. So obviously the 35 prediction is much further away from the data. They're both extrapolation, but this one's a further extrapolation, and the further away you are from the data set, the less reliable. So if I have to pick one of these that I have the more confidence in, it's going to be the first one. So we have the more confidence in the 2025 prediction of the 272.83 billion because it is closer to the data set. It's still extrapolation, it's just the near extrapolation versus the far extrapolation.